In this lab, we recorded on video the motion of a cart with wheels that slid on a track. We tracked the cart's position with time and plotted values on a position time graph. We then created another position time graph using a Python GlowScript model and compared the model to the actual results. The objective of this lab was to compare the cart's actual motion to its supposed motion if it was in an ideal scenario without forces like drag and friction. We discovered that the position time graph of the ideal scenario is a straight line with positive gradient passing through the origin, and that the actual position time graph resembled a y is equal to sine squared x graph instead. The key principle used in this lab is Newton's first law, which states that an object's velocity will stay unchanged provided the net force acting on it has a magnitude of 0 newtons. Let's begin with a free body diagram. In this picture, there's a cart sliding on a track. The cart is our system. Let's assume the cart is moving at v meters per second to the right. In an ideal scenario, there are only two forces acting on the cart: weight and the combined normal force from the track acting on the wheels, indicated by sigma n. The cart's vertical position is not changing, so sigma n is equal to mg, and the net y force component is 0. There is no friction or drag causing the cart to decelerate, so the net x force component is also 0. The magnitude of the z component is 0 as well. Newton's first law indicates that the cart will continue to move at v meters per second to the right, given that the net force acting on it has a magnitude of 0 newtons. The rate at which the cart's position is changing is constant, so our position time graph would be a straight positive gradient line. In a practical scenario, some things change. Sigma n still equals to mg, and the y and z components of the net force acting on the cart remain 0. But the x component is now negative due to the presence of drag and internal friction from bearings and axles. If the magnitude of the combined drag and internal friction forces is given by a variable k, then the net force acting on the cart is as follows. To be clear, the surroundings of this system are the air and the track. The source of dynamic friction is not from the wheels contacting the track, but from internal friction from within the cart itself due to mechanical components rubbing against each other. Let's talk about the position time graph for this scenario. At time t is equal to 0 seconds, someone pushes the cart, causing it to momentarily accelerate, but then immediately start decelerating due to the presence of internal dynamic friction and drag. So, the gradient of the position time graph is initially 0, it then increases, then decreases, and then becomes 0 again as the block comes to rest. The function f of t is equal to sine squared t accurately predicts such behavior. As said earlier, we recorded the motion of the cart and tracked its position frame by frame using a software called Tracker. We obtained a table of values of position in meters versus time in seconds and plotted that data in Excel. We then found the average velocity using this formula. We substituted the average velocity, initial position, and total length of the time interval into the starter code and obtained a straight line graph model for position versus time. It's worth noting that there were two problems with our procedure. Firstly, I held the camera in my hand and the camera did move because holding a camera steady above the cart and track setup was hard. This made measurements harder and less accurate. A fixed tripod setup perpendicular to the track would have been ideal to remove parallax error. Secondly, it's not entirely accurate to manually track the position of an object even in a software. I would have ideally used an AI-enabled object tracking software like TensorFlow instead. This graph shows both the actual results in blue and the results generated by the GlowScript model in orange. In the actual results, the cart initially accelerates slightly and then decelerates, evident from the increasing and decreasing gradients. The model generated by GlowScript is much simpler, however, and assumes that the cart is moving at a constant velocity of about 0.57 meters per second throughout the entire duration of the time interval. The code essentially uses the position update formula and incrementally predicts the next position in a while loop. Given that this code uses an ideal model where the net force acting on the cart is 0,0,0 newtons, the code does not need to know the magnitude of any other forces or even the mass of the cart itself. We selected this segment of the time interval in particular since, while the actual position time graph is not linear, it appears to be more linear within the smaller interval.